Last time, Dijkstra found the fastest route, but look how it searched. It spread out in every direction like ripples in a pond, exploring nodes far away from the goal, even behind the start. For a map, that's wasteful. For a game character chasing you in real time, it's a disaster. A star fixes that by giving the search a sense of direction. It finds the exact same shortest path, but explores a tiny fraction of the nodes. It's the pathfinding algorithm in games, robotics, and GPS, and once you see the trick, it's almost obvious. This is Logic Lab, where computer science becomes something you can see. Today, shortest paths again, but this time the search has a hunch about where the goal is. Quick recap. Dijkstra always expands the node that's cheapest to reach so far. That's safe and correct, but it has no idea where the goal is, so it happily explores in the wrong direction, settling nodes it will never need. But usually you do know where the goal is, its coordinates on the map. So why explore backwards? We'd love to bias the search toward the goal while still guaranteeing the best path. That's exactly what A* does. The trick is a heuristic, call it H for each node. H is a cheap estimate of how far it still is from the goal. On a map, the obvious one is the straight line distance, as the crow flies. It's just a hunch. The real route might be longer, walls and one-way streets get in the way, but the straight line guess always points roughly toward the goal. That's the compass A* steers by. Now the heart of A*, one little formula. F equals G plus H here. G is the real cost to reach this node so far, that's Dijkstra's part. And H is the estimated cost from this node to the goal, the hunch. Dijkstra picked the node with the smallest G. A*, instead picks the smallest F, balancing how far you've already come against how far you probably still have to go. That one change is the whole algorithm. And the effect is striking. Side by side on the same grid, Dijkstra fans out into a huge circular blob, while a star carves a narrow corridor straight toward the goal. Same optimal path at the end, a fraction of the nodes explored. There's one rule that keeps it honest. The heuristic must be admissible. It must never overestimate the true remaining cost. As long as it never lies high, A* is guaranteed to return the optimal path, just like Dijkstra. And notice the spectrum. If the heuristic is 0, no hunch at all, A* becomes exactly Dijkstra. The more accurate your honest heuristic, the more sharply the search aims and the less it explores. Heuristic quality is the dial between blind and laser-focused. Where you'll meet it. Pathfinding in nearly every game with a moving enemy or unit, robot and drone navigation, GPS with smart shortcuts, and classic puzzle solvers like the sliding tile puzzle. The whole art of A* is choosing the heuristic, informative enough to guide the search hard toward the goal, but honest enough to never overestimate, so you stay both fast and optimal. Recap. Dijkstra explores blindly in all directions. A star adds a heuristic H, an estimate of the distance left, and picks the node with the smallest F equals G plus H. Keep H admissible, and you get Dijkstra's optimal path while exploring a fraction of the nodes. H equals 0 is just Dijkstra. So far we've searched maps, networks of places, but some problems are a search through a tree of choices where an opponent is fighting back. How does a computer play a perfect game? That's next on Logic Lab. See you there.